Welcome to the today's session. Today we are discussing about the microcontrollers as microcontrollers are the heart of the embedded system. So let's start the microcontroller 8051. Microcontrollers are divided into various categories based on its memory size, architecture, bit, and instruction sets. These are some classifications of the microcontroller. There are 8-bit microcontroller, 16-bit microcontroller, 32-bit microcontroller. For example, 8-bit microcontroller is 8051, and in case of 16-bit microcontroller, the example is Intel 8096. It is a 16-bit microcontroller, and in case of 32 by 30, there are 32-bit microcontrollers are also available. Generally, 32-bit microcontrollers are used for automatic operational machines, medical appliances. In this case of embedded system, generally we are using the 32-bit microcontrollers. Otherwise, we can use the 8-bit or 16-bit microcontrollers. So this is the classification of microcontrollers according to the number of bits processed by the processor simultaneously. Next, the classification can be done using the based on the memory. The external memory of this type of microcontroller is designed in such a way that they do not have a program memory on the chip, and hence it is named as the external memory microcontroller. For example, the Intel 8031 is a microcontroller, and in this microcontroller there are no internal program memory. And in case of embedded memory microcontroller, this type of microcontroller is designed in such a way that the microcontroller has all programs and data memory. Counters and timers, interrupt, IO ports are embedded on the same chip. For example, 8051 is the microcontroller which consists RAM, the ROM, and there are interrupt controller, there are IO ports, and there are timer to timer counter inside the same chip. So depending on this external memory, we can also classify the microcontrollers. Now, based on the instruction set, we can also classify the microcontroller by RISC and CISC processor. RISC stands for Reduced Instruction Set Computer, and CISC stands for the Complex Instruction Set Computer. The difference between the reduced instruction set computer and the complex instruction set computer is very important for the semester, or it is very important to know the difference between the two architecture of the microcontroller. So first of all, we know the full form of RISC and CISC. RISC processor have simple instructions taking about one clock cycle, and in case of CISC processor has complex instruction that they take up multiple clock cycles for execution. In case of RISC architecture, the performance is optimized with more focus on the software, and the performance optimized with focus on the hardware. That means in case of if we compare CISC and RISC processor, the more number of operation can be done by the hardware in case of CISC processor. On the other hand, in case of RISC processor, the same kind of operation can be done using the software, that means through instructions. And as the name suggests, RISC means reduced instruction set. So the set of instruction, the number of instruction for RISC instruction in RISC processor will be very small. That means set of instruction is limited. On the other hand, the instruction set has variety of different instruction that can be used for complex operations. So there is a difference between the size of the instruction set in these two type of microcontrollers. Complex addressing modes are synthesized using the software, as I have told you that uh, much more many operations can be done using software as well as hardware. But when we consider the RISC processor, the we are optimize, or we are doing the operation using software than the hardware. But in case of RISC processor, we are doing that kind of operation using the hardware. So RISC processor are highly pipelined, and there are normally not pipelined or less pipelined in case of CISC processor. We have learned about the pipelined architecture. What is pipelined? Again, I can give an idea that pipelines means there are more than one processing unit. For example, if we consider 8086, there are two units: BIU unit, that means bus interfacing unit, and the other is execution unit. So when the execution unit will execute one instruction, at the same time the BIU unit fetch the next instruction from the memory, and it will store the instruction in its 6 byte queue, right? So when the execution unit complete current instruction, in that case it will directly fetch the instruction from the queue which is internal to the processor. So the process will be very fast. The processing speed will be increased if we support the pipelined architecture, which is available in case of RISC processor. The most common RISC microprocessor are Alpha, ARC, ARM, AVR, Spark. These are the most PIC, PIC. These are the very important example of the RISC processor or RISC architecture. And on the other hand, the system 360 VAX, PDP 11, Motorola 68000 family, AMD and Intel 86 CPU. These are the example of the CISC processor. So you have to study the difference between the RISC and CISC processor, because it is very important to understand the, it is very important for the understanding the different kinds of microcontrollers available in the market. Now I am going directly to discussing the architecture of 8051. The silent feature of 8051 microcontroller are it is a 8-bit CPU. That means it can simultaneously process 8 bits. On the there is a on-chip clock oscillator. There is a 4 kilobyte, as we know that in case of microcontroller there are RAM and ROM uh, on the same chip as the processor. So in this case, in case of 805, there is a 4 kilobyte internal program memory, which can also be known as code memory or the instruction memory. And basically it is a ROM, because ROM is a non-volatile memory. So basically when we are using the embedded system, we are using the system for a fixed purpose. In that case, there is no need to alter the code every time. So we just code the we just write down the instruction or we just write down the coding inside the ROM, so that it is always inside the ROM, and it will repeatedly executed the same operation, because we are doing the same kind repeat say fixed type of operation repeatedly repeatedly in the embedded system. So that is why we are store our code or instruction in the inside the program memory. There is also an 128 byte of internal data memory, which is the basically the RAM. We can but it is obvious question that if my program, or if my instruction if my code is more than 4 kilobyte, in that case what will happen? In that case we can connect the 60 external 65 64 kilobyte ROM with the 8051. Similarly, if we need more RAM, in that case also we can connect 64 kilobyte external RAM as a data memory with the 8051. There are five vector interrupt structure. Reset, in this case reset is not considered at the interrupt. Okay. We will discuss the different or five interrupts and their priority in later. Okay. So 8051 CPU consists of a 8-bit ALU with associated registers like accumulator, register B, PSW, 16-bit program counter, and stack pointer. Basically all these are same as we have studied. In case of the purpose of the register are almost same as the purpose of the accumulator, register B, PSW, 16-bit program counter, stack pointer in case of 8085. But we will discuss these registers in our next slides. I have to mention one thing, that in case of 8085 we will not directly do the multiplication or division operation, but in case of 8051 we can do the multiplication and division operation directly, because instructions are available, and in that case register B is used for the multiplication and division purpose. So there is a special use of the register B in case of 8051. And the next one, the ALU can perform the arithmetic and logic function on 8-bit variables. It is quite obvious, because as the processor is a 8-bit processor. Now there are 32-bit bidirectional IO lines, because there are 4 IO ports are available in case of 8051, and all 4 IO ports are 8-bit ports. So that is why there are 32-bit bidirectional IO lines are available in case of 8051. There are two 16-bit timer counter also available in case of 8051, that are denoted by T0 and T1. There is a full duplex serial transmitter receiver are also available in case of 8051. 4 register banks with 8 register in each bank is also available. Basically these 4 register banks with 8 register in each bank supports the fast context switching. That means when the processor is doing something, suppose doing task number 1, it will suppose it will be interrupted by the task number 2. In that case, when the processor transfer its job from task 1 to task 2, in that case it will store the temporary data and the address location of the next instruction of task 1 2 in any register bank, so that when it will come back from task 2, it will directly fetch the all the information it needs to restart the task 1 from that particular register bank. And as the register banks are inside the IC, that means 8051 IC, that is why to retrieve all the information from the register banks is very much fast. So that is why when we switch from one context to the another context, that means from task 1 to task 2, the context switching is very fast if we use the register banks, rather than if the processor will uh, store the same information, that means the temporary data, address, location of the next instruction to the external memory. In that case it will need more time. So that is why processing speed increases if the processor will store the temporary data or the next instruction register, next instruction address to any internal register banks. So it is very useful for the context switching. I think context switching is clear. Context switching means when we switch from one task to another task. In that case, before switching, we processor will store the information of the current process to the memory location, and when it come back from the second task to first task, it will retrieve all the required information from the particular register bank. This is known as context switching. And for context switching, register bank, if there are more number of register bank, in that case it is easier for context switching, and it will increase the speed of operation. Okay, so this is the there are four register banks inside 8051, and each register banks contains 8 register. There is a 16-bit program counter, there is a data pointer, 16-bit data pointer, dptr. This dptr, the data pointer, can be used as dptr high and dptr low. In that case it will behave as an 8-bit register. There is a 8-bit program status word, which is known as PSW, and there is a 8-bit stack pointer, and we know that the stack pointer will point out the address of the stack. We will discuss all these register in detail in the next few slides. Okay. So this is the block diagram of the 8051. In this case, this is the system bus or internal bus. These all are system bus or internal bus. This is your bus control unit. This is the oscillations unit. This is your CPU, interrupt control, and these are these are external. There are external interrupts also available. External, basically there are external and internal, both type of interrupts are available in case of 8051. There is a 5 kilobyte ROM inside the same IC, and there is a 128 kilobyte RAM, and there are two timer counter section are in 8051. This is the serial communication section. This is the transmission. TXD means this is the transmission, serial transmission pin, and this TRXD means this is the serial receiving pin. There are four 8-bit ports are available: P0, P1, P2 and P3. And in case of 8051, the ports are multifunction purpose, that used for multifunction purpose. That means it is not only used for only for IO operation. They can be used for other operations also. So this is the block diagram of 8051. As I have said that in case of 8051 there is a 4 kilobyte internal ROM. The address space is from starting from 000 hex to 0FF, that means triple F hex. If the program size, as I have said, that if the program size is more than 4 kilobyte, in that case we have to connect or interface the external program memory with the 8051, and the connection we will do later. Okay. There is a 8-bit accumulator register, and it is widely used for arithmetic logical operations. Accumulator is also used to transfer data between external memory. Register B, because I have already said that register B has an extra facilities in case of 8051, that is, along with the accumulator, it is used for multiplication and division operation. So these two register, that means accumulator and register B, together are also called as math registers. There is another register which is known as a program status word. We know that program status word basically holds the flag bits, and in case of 8051 there are 8 flag bits. That means the flag register is a 8-bit register, but among the 8 bits only 6 bits are used for 6 bits are used as the flag bits. First one is the carry flag. AC means auxiliary carry flag. F0 is used, or it can be available to the user for general purpose operation. RS1 and RS0, these two flag bits are used to select the register banks, because we know that there are four banks are available, register banks are available in case of 8051. So to select 4 banks, we need at least 2 pins or 2 bits to select the 4 register pins, banks, because 2 to the power 2 means 4. That is why we need at least 2 bits to select the 4 banks. That is why RS1 and RS0 used to select the register banks. OV, that means such overflow flag, and P is the parity flag. Now, I have told that there are among the 8 bits, there are only 6 bits are used for flag registering flag as a flag register bits. So these, in case of, there is another facility, extra facility in case of 8051. That means here we can access each bit of the PSW. That means the flag, we can access the flag bits of the flag register. So first one, the carry flag. This is same as the carry flag used in 8085. So it is the 7th bit of the program status word register. It is set if the carry is generated from the after any arithmetical logical operation. If carry is generated from the D7 bit, in that case the carry bit is in the set condition, otherwise it is in the reset condition. Auxiliary carry, this is the PSW.6, that means it is the D6 bit of the flag register. If there is a carry from D3 to D4 during any addition or subtraction operation, in that case the carry flag is set, otherwise it is in the reset condition or it is cleared. Generally, auxiliary carry flag is used for uh, decimal adjust in BCD addition or subtraction operation. So here we are taking an example. The example is that, suppose we want to add 1 double triple zero, then 1001. So this the digits 76543210 written in red color indicates the bits number, and these are the bits. Suppose this is my first number and this is my second number, and we want to add these two number. So when we want to add these two number, 1 plus 1 means 0. 1 is carry, so this is your 1, and then the next bit is 0 and 0, so 0 0. And when we consider that when we add the d3 bit, in that case there is 1 1, so when we add this to 1, there is a 0 and there is a carry is generated, and it will transfer to d4 bit. As the carry is generated from D3 bit and transferred to D4 bit, that is why after this addition operation, the carry flag, the auxiliary carry flag is in the set condition. Otherwise, if this type of carry is not generated from D3 to D4, in that case the carry auxiliary carry flag is in the reset condition. Next one is the, so this is the operation, addition operation, and if this is my result, so from this result section we can also say that as there is no carry generated due to addition, so after this addition operation the carry flag is obviously in the reset condition, that means carry flag is cleared. Okay. So now next one is your parity flag. If we consider the parity flag, it is not PSW0. We know that the auxiliary, the accumulator register contains the result after any addition, subtraction, or logical operation, and if the number of ones in the mm, accumulator is equal to an odd number, in that case the parity flag is in the set condition, otherwise the parity flag is in the reset condition. So if we consider this example, the result contains 1 2 3 4 5 ones, right? That means it will contains a odd number of ones. So after this addition operation, the parity flag will be in the set, it will be in set condition. Okay, so this is all about parity flag. There is another important flag, that is your overflow flag. This flag is used for signed arithmetic. We know what is signed arithmetic. In case of we know that in digital notation, that means when we want to represent any number in digital format, in that case we can represent the number in signed magnitude format. That means the D7 bit is reserved to indicate the sign of the number. In that case, rest of the 7 bit will indicate the magnitude of the number, and if D7 bit is equal to 1, that indicates the number is negative, and if D7 bit is 0, in that case it will indicate the number is positive. So basically this overflow flag is used in the signed arithmetic operation. If the flag is set, so if we are using the signed arithmetic, that means we are taking two numbers which are signed numbers. In that case, the result of a signed number operation is too large and causing the higher order bit to overflow into the sign bit. That means after addition, suppose we are adding two signed numbers, and if the d6 bit of the two numbers equal to for example 1, in that case when we add these two numbers, that means d6 bits of the two numbers, in that case 1 plus 1 means 0, so it will generate a 1 which is overflow to the d7 bit. And we know that in case of signed arithmetic, d7 is reserved for sign operation, it will indicate the sign. But here when we are adding the two number, basically a carry is generated from d6 bit to d7 bit, that means it will overflow the sign bit, right? In that case, the overflow flag is in the set condition, and otherwise the overflow flag is in the reset condition. So this flag is generally used for signed arithmetic. So these are the 1, 2, 3, 4 flags, and the other two flags, RS1 and RS0, is used for the for selecting the register banks. So this is all about the PSW bits of the 8051. So the other two bits are RS0 and RS1, and as we know that in case of PSW we can access, or programmer can access the individual bit. So using the set and clear instructions, or using the instructions of 8051, we can set particular bit of the particular RSW, RS1 or RS0 of PSW register, to select any register bank. For example, if we keep RS1, RS0 is equal to 00, in that case register bank 0 is selected. If we keep RS1 is 1 and RS0 is equal to 0, in that case register bank 2 is selected, and if we keep 1 1, in that case register bank 3 is selected. So using the instruction, a programmer can set or reset the RS1 or RS0 bit of the PSW register, and they can select any one of the register banks available in 8051. So almost this is we have discussed the three register of 8051. One is accumulator, which is used for addition, any kind of arithmetic or logical operation, and the register B, which is again a special, there is a special function of register B. It can be used as a simple register, or it can be used, it must be used in time, in case of multiplication and division operation. That is why these two registers in 8051 is known as the math registers. And the another important register of 8051 is, that is the PSW register. And there are eight, it is again a 8-bit register, and among the 8-bit register only the 6 bits are used, and one of the 6 bit is used for the programmer, according to according to the programmer choice. They can use that, or they can program that particular bit, and rest of the 5 bits also can be programmed, but the function of the bits are specified. For example, carry is set when the after any addition or subtraction operation, if carry is generated, in that case only the carry bit is set, or otherwise it is cleared. Or manually, using the instruction set and clear instruction, we can set or reset the carry flag also. And there the other function of auxiliary carry, parity, and parity are almost same as 8085, and there is an extra flag which is overflow flag. And the overflow flag is basically used for signed arithmetic. We have also discussed what is signed arithmetic. In case of signed arithmetic, the most significant bit, that means the D7 bit is used for indicating the sign of the number. If it is 1, in that case the number is negative, and if it is 0, in that case the number is positive. And in this case, in the rest of the, because we are considering 808, it is any register contains 8-bit number. So if we specify D7 bit is used for the sign, to indicate the sign of the number, in that case rest of the bit, that means starting from D0 to D6, this 7 bit basically indicates the magnitude of the number. So this is almost 3 register we are discussing for 8051. Rest of the registers and the other portion of the 80, the other portion of the 8051 we will discuss in the next class. So thank you. There are three registers or important registers are also available for 8051, which is almost the function of the registers stack pointer and program counter is same as the 8085 or any other kind of register, but in this case the stack pointer contains the address of the data item on the top of the stack. Stack may reside anywhere in the internal RAM. We can manually set the address of the address of the um, starting of the stack. We can set manually set by programming. We can set the starting address of the stack, and on reset the stack pointer is initialized to 07 hex, so that the default stack will start from the address 0811. That means the difference between 8085 and 8051 is that in case of 8085, the stack pointer contains the maximum highest address of the stack, and when the data is pushed on the stack, in that case the stack pointer decremented first, then the data will be um, data will be entered into the stack location. But in this case the process is somewhat to reverse, because in this case the stack pointers, for example stack pointer contains the starting address which is 07 hex, and the first location where we want to store the data, that is 08 hex. That means in this case the first stack pointer increased by 1, and then the data will be pushed into the into that particular memory location or inside the stack. So in this case the stack pointer incremented by 1, not decremented by 1. The stack pointer incremented by 1, and the other difference is that in case of 8085 we know that the stack pointer address is 16 bit, but in this case the stack pointer address is 8 bit address, and it is the internal, it is the portion of the, it can be in any portion of the internal RAM, and manually we can set the address. But the default stack pointer address, that means when we just power on the device, the microcontroller, in that case the the default stack pointer content will be 07 hex. The program counter is also same as the 8085. It will contain the address of the next instruction to be executed. On reset the PC means on reset PC means program counter. Reset means when we are resetting the microprocessor or just switch on the processor. In that case the program counter will be cleared, and after fetching every instruction program counter is incremented by 1, same as 8085. And there is another register which is known as the DPTR, that means data pointer. This is a 16-bit register, but we can use this as a 2 8-bit register. In that case we can say the DPH, that means data pointer high byte, and DPL, that means data pointer lower byte. This is a 16-bit register which is used to furnish the address information of the internal and external program memory and for the external data memory. Okay, so this is almost all about the important registers inside the 8051.